For discrete probability distributions, I want to introduce three of them. They are widely used and they should be good enough for your for daily work or daily research, of course. And the first one is called binomial distribution. Okay, for example, the annual probability of flooding in a community is 0.25. What is the probability of 3 floods in the next 3 years? In order to solve this problem, we need to use binomial distribution. Okay. So the next one is geometric distribution. For example, the annual probability of flooding in a community is 0.25. What is the probability that the next flood occurs 3 years later from now? Okay, here I only listed examples, right? About the definition or the details of this distributions, I will introduce them later one by one. So do not worry, okay? I'll just use some examples to give you some ideas about what scenario a distribution should be applied to, okay? So the third distribution is called Poisson distribution. Poisson is a French word, okay? It's the name of a very famous mathematician from France, right? Of course. So example for Poisson distribution. Suppose that traffic accidents occur on average once every 10 days. Okay, so here we have a relative frequency here, 1 in every 10 days. What is the probability that there are 3 accidents during the next 5-day period? So we know the relative frequency for a 10 days period. That's what we know. That was we found from history. And what is the probability that there are 3 accidents in the next 5-day period, not 10-day period? Okay, let me just introduce these distributions one by one with examples. First, binomial distribution. The process of interest consists of n independent trials, or you can say n independent experiment. Trials, experiments, they are the same thing. Each trial results in one of 2 possible outcomes. That's the reason why this distribution is called binomial. It's yes or no, success, failure, 0, 1. No matter what, only binary outcomes or 2 possible outcomes. So the probability of success is constant, which means stays the same, and equal to P on each trial. Okay, so the random variable of interest is the number of successes out of n independent trials. Okay, which means we're going to repeat a trial multiple times, say n times. And for each trial, there are 2 possible outcomes, success or failure. Okay, and the probability of success is a constant and it is P. Okay, so like this example, the annual probability of flooding in a community is 0.25. You can consider this as P, the successful rate. I'm not saying that flooding is a good thing. Let's just be neutral here. If flooding is an experiment, and yes, there is flooding, this fact can be considered as a quote success unquote, okay? And the probability for that is 0.25. So what is the probability of 3 floods in the next 4 years? You can address this question, this problem using binomial distribution. Okay, how to do that? The formula. Part 1, you need to calculate combination. So selecting X trials from a total of N trials. Of course, X trials, they are successful trials. And part 2, the probability of the selected X trials being success, and the rest of the N minus X trials being failure. So this is a formula. So let's just say we have done N trials, right? And I want to calculate the probability of X trials being successful. How to calculate the actual probability? You use this function. Okay. So firstly, combination. This large parenthesis. We have done N trials, and X of them are successful. And then you multiplicate P to the power of X. P is the probability of success. X is the number of success. Then you multiplicate 1 minus P to the power of N minus X. This makes sense, right? If the success probability is P, then this part, unsuccess or failure probability is 1 minus P. And how many times? N minus X times, because there were N trials and X of them were success, then N minus X, the rest trials, they were failure, okay? So this is the formula. So let's just talk about this resident example. Random variable, we call it X. It's the number of new households among N surveyed households. Okay, the total number of surveyed households is 4. So the probability that a surveyed household is new one is equal to P equals 0.2. So what does it mean? It means that we surveyed 4 households. Okay, and we care about how many of these households are new households. And the probability of finding a new household is 0.2, which is not too high, right? So we need to find the probability that exactly two surveyed households are newcomers or new households. That is, find the value of P when X equals 2. Okay, so this is a problem you need to solve. Obviously, this is a binomial distribution problem because there is something called success, which is finding a new household, and failure, finding an old household, right? And we also know that we did 4 surveys, N equals 4. And we also know that the probability of success or finding a new household is 0.2. So everything is ready here. We just need to use the formula I just introduced to finish the calculation. So step 1, combination, NX. So we did survey for 4 households. So N equals 4, and we want to find out the probability of that 2 surveyed houses are newcomers, which means that they are 2 successes. Okay, so N equals 4, X equals 2, right? So you use the formula I provided in previous lecture. You find out the combination is 6. And then the probability of 2 trials being success and 2 trials being failure. So P to the power of X multiply 1 minus P to the power of N minus X. So P is 0.2, right? And to the power of 2, which means square, 2 success. And the probability of failure is 0.8 to the power of 2. Because if there were 2 success, then there were 2 failure. So yeah, this is exactly what you want to calculate. And then you just connect them, right? So 6 multiply 0.2 to the power of 2 multiply 0.8 to the power of 2. Eventually, you have the result here, 0.1536, which means that the probability that 2 surveyed households are newcomers is 0.1536. Okay, this is a very simple example. You can also find it in your textbook of, of, of the associated chapter. And what I suggest here is not only reading this slide and watching the video. Get a pen, get a piece of paper, try to calculate this combination by yourself. Okay, make some hands-on experience, calculate the probability by yourself, and say the result from yourself is consistent with the result here on this slide. Okay, okay, that's binomial distribution. Next, geometric distribution. The process of interest consists of independent trials. Each trial results in one of two possible outcomes, success or failure. This is consistent with the binomial distribution we just introduced, right? The probability of success is constant and equal to P on each trial. This is also the same as binomial distribution. The random variable of interest is the number of trials on which the first success occurs, not how many times a success happened. That was for binomial distribution. Here, in geometric distribution, we only care about the first trial that was success. Okay, the formula here is very simple. The first success occurs on the X trial. Okay, you did multiple trials, and one was the first successful trial happening. It could be the first one, could be the second one, could be the Xth one, right? And the first X minus trials are all failures, of course, because if the X trial was the first one that was successful, then all trials before that trial, they were failures. How many failures were there before the X trial? X minus 1 trials, of course. So this is the formula, 1 minus P to the power of X minus 1. That's the probability for all those X1 failed trials to happen. Then multiply P. P is the probability for that first successful trial. Okay, so that's it. There is no even combination to be concerned about. So example here. Again, the resident example, okay? The probability that an individual moving to another place in each year is constant and equal to 0.18. Okay, the probability an individual is going to move from one city to another or a part of the city to another part of the city. So random variable here is X, okay? The number of years it will take for an individual to move from now on. Because for each year, there is a probability, which is 0.18, that one individual will move. But it's more likely that it will just stay there, right? So we care about the number of years it will take for an individual to move. Okay, so find the probability that an individual's next move will occur on the X year from now on. That is, find the value of P X equals lowercase x. So what's the what's the probability of success here? Is 0.18. Obviously, we consider moving as a success, quote, success, unquote. Okay, so and not moving, of course, being failure here, right? So before a success is happening, before a moving happens, all those years this individual does not move, they are all failures, right? So you simply use this equation to make this table. So for X equals 1, which means that individual will just move this year. So here, the probability is P. because if x equals 1, then this part is equal to the power of 0, which means the result is 1. So 1 multiplied p is p. So this is the equation, right? And if you, this is the specific calculation, right? 0.82 being the probability of failure, right? To the power of 0, and then multiply p. So this is the result if x equals 1. And if x equals 2, 3, 4, 5, you can simply replace, you can just adjust this formula accordingly, right? So the probability that an individual's next move will occur on the third year is what? Is 0.1210, which means that for the first 2 years, this individual does not move. X equals 3, right? 3 minus 1 equals 2. And in the third year, this individual moves. So that's P. Okay, 1 minus P to the power of 2, then multiply P. Okay, so this is a result. This is a result, 0.1210. So you can see that a very convenient feature for discrete variable is that you can simply use a table, could be a very big one, but you can use a table to just address probability one by one by each possible value of your random variable. For example, here, x could be 1, could be 2, could be 3, 4, 5, or even 6, 7. You can just extend this table indefinitely. A person could just live at a specific location for 50 years and then move on the next year, on the 51st year. Of course, you can simply replace x by 50 or 51, and you can still use this very simple formula to calculate the probability that an individual will live at a place for 50 years and move on the 51st year, given this probability of moving. Okay, so this is geometric distribution. The special part about this distribution is that we only care about the first success. Okay, the first success. The last one distribution I want to introduce here is called Poisson distribution. The process of interest consists of events that occur repeatedly and randomly over space of time. And events are independent of past or future occurrences. The occurrence of an event within a specific period has a constant mean rate or density equal to lambda, or relative frequency. Okay, and we use lambda to address that constant mean rate or density. And the random variable of interest is the number of events occurring during a certain time period or across a particular area. So the random variable here is the number of events happening within a specific range. This range could be a time period, could be a particular area. The formula here is a little bit more complex. A fractal, the factorial of x is a denominator, right? Which is x is a random variable, right? So the number of events occurring within a specific period, right? And the numerator is e to the power of negative lambda, and e is equal to 2.71828. It's a constant. Then multiply lambda to the power of x. Okay, we want to know the probability of a specific number of events occurring within a time period. and the number of events is addressed by lowercase x. Okay, so example here. So let's just say the mean number of accidents during the 30-day period is constant and equal to lambda equals 1.5. Okay, this mean number of accidents is for a 30-day period. Okay, this is very important. It's not for 40 days, not for 10 days, it's for 30 days. And the random variable x is the number of accidents occurred during the 30-day period. Find the probability observing x accidents during the 30-day period. That is, find the value of p, what? Uppercase x equals lowercase x. So we use this formula I just mentioned, and you still can use a table to do that. So if x equals 1, what does it mean? It means I want to find the probability observing only one accident during a 30-day period. So you just replace x by 1, and then lambda is a constant, which is 1.5. Then you just use this formula to calculate e to the power of negative 1.5, which is lambda, and multiply 1.5 to the power of x. X is 1. So this is a result. So 0.3347 is the probability of finding only one accident during a 30-day period based on the historic data that there is 1.5 accidents for a 30-day period. Okay. So of course you can change x to 2 to 3 to find the probability for observing or observing or finding out 2, 3, or 4 or 5 accidents during the 30-day period. Okay, you simply replace x. But lambda here is the constant because we're always talking about this 30-day period for all the 3 values, 1, 2, or 3. Because this lambda 1.5 is based on a 30-day period. So let me ask, how about I change 30-day period to a 60-day period? Do we still use this 1.5 for the value of lambda? No. If there were, if averagely there should be 1.5 accidents in a 30-day period, then we should consider that averagely there should be 3 accidents in a 60-day period, right? We double the period, we double lambda. So lambda here should be 3.0, okay, instead of 1.5. Okay, so lambda is the tricky part here. You should be very clear about how this lambda value was calculated, was generated. 1.5 here is based on a 30-day period. If the period has been doubled, then you should also double lambda. If I change this 30-day period to 45-day period, then you should multiply lambda value by 1.5 because 45-day period is 1.5 times longer than 30-day period, right? Okay, so here you change the lambda from 1.5 to 3.0. For the rest of the calculation, everything else stays the same. If you say x equals 1, then sure. It means that find the probability observing only one accident during the 60-day period. It's still one accident. X still equals 1. But here you need to change lambda because it's 60-day period, not 30-day period. Okay, that's the only tricky part. And this is the end of this lecture. You can say that I introduced 3 types of probability distributions for discrete random variables. And for next lecture, I'm going to introduce probability distribution for continuous random variables. Okay, thank you. I will see you later.